Now we switch topic and discuss sample size determination. In two-stage cluster sampling, we have two different sample sizes, right? So Ni, so one component is the sample size for stage 1, which is Ni, and sample size for stage 2, M. So these two components we need to determine, and the tricky part is that there's a two type of cost. One is the selecting cluster, right? So selecting cluster will mean cluster can be a town or a county, and then so if you go to some county in different place, then you have some so kind of gas and mileage expense, so something like that, or interviewer, salary, something like that. So this is cost for selecting cluster, and then there's additional cost for actually visiting the individual, the element, and then obtain the survey result, right? So that's another cost. So we may have so the cost function is actually like this. So C1 times Ni and C2 times Ni times M. So this is the cost for visiting cluster, like gas, mileage, and so forth, right? And this is more like a incentive, survey incentive. When you do survey, we don't get a survey result for free. We pay for the time, compensating the time of the interviewee. So that's another cost. So this is cost function. Okay, and then the natural question is, given the total cost, we should find N1 and M that minimizes the variance of y bar. And we already obtained this variance formula, right? So between and within, and between we have 1 over m part, and within we have 1 over Ni times m part, small m part, and then we have a final correction. So here we ignore this Ni because capital Ni is really quite large, very large, so we can just ignore this. Okay, so now how to solve this problem? Well, there's some interesting result. So one thing you notice that the Ni part, so this Ni part, so everything is 1 over Ni here in the variance, and then cost, you also have Ni terms here. So if you multiply V and C, variance, and so this variance means variance of y bar. So if you multiply V times C, then you actually have Ni cancels to each other. So it's free of Ni. So it's only, what is left is only M. And here this is M here, right? We have M here. So you expand this, you end up getting this form. Okay, so constant means that it is a free of M. So so we are interested in finding M, so we don't really care about this constant. So how can we find the minimize? So when optimal M that minimize this variance times C. So why it's okay? Because the problem is minimize variance subject to C constant, right? That's same as minimizing variance times C subject to constant. So it doesn't matter. Okay, so that's what we have here. and so you to solve this, we use this inequality. So this is a mathematical inequality, and the interesting part is that the equality here, the lower bound, is achieved when we set these two terms equal to each other. So two terms are equal, then we have inequality. We have equality here. So that's what we are going to use. So basically, the equality here. So we have two terms basically. We have one term here, another term here, right? So we set these two equal. So C1 S square over S within square over 1 over M equal C2 S SB square, right? SB square minus S within square divided by M times M. Okay. So we create this. Then it's same as saying that M equals to C1 over C2 times S within square divided by SB square minus S within square divided by M. Something like that. Okay. So that's what we have here. Okay. And then the next one is we use this, we want to express, law, right? We want to express S within and SB between using the expression based on the intra-cluster correlation. So you plug in this to here, and here, right? And then simplify, then you end up getting this form. So which is interesting, because if rho is close to 1, that means what? Rho is close to 1, that means the intra-cluster correlation is high. That means the every element in the cluster are similar to each other, right? So quite homogeneous. So then there's no point of selecting many elements in the same cluster. So M, it makes sense to M stack to be low, because small number is enough. So that's that kind of makes sense in this. So this formula is kind of makes sense. And then once you have a smaller M star, then you have an increase Ni star. So you select more clusters than element. So that kind of makes sense.